I have something that's quite interesting, which is a PiGame module, and I tried to do an M-body simulation of a galaxy merger over the weekend on my laptop, and it works quite nicely. So I thought I'd export it over onto the PC. But when I run it, it looks like this. So I'm just about to run it, and I kind of like, okay, there was 75 loops. I might make the loops bigger, and I'll go through the code as well. But I've got to try and troubleshoot this. So down in the code somewhere, I set the number of particles in the system and also the screen size. And it's probably more apparent if the screen size is bigger. So I'm going to make 1000 by 1000 screen, and let's just make 50 particles like this. And if I hit the F5 button to run it, what we see is those white lines that appear in between. And actually, I put something else in at the end of the loop, just a counter here. Let's just make it run 250 times, just so it's a bit clearer for the purpose of the video and what's going to happen. All that happens here basically is that, and I'll be going through this anyway, is that I put a counter in here, and what actually happens is, like with all the various different game systems, they do this drawing loop of some kind, whichever their way is. So PiGame has its own. It's the PiGame draw or PiGame display update, and it keeps on updating. And it runs in this while loop, and what I do is I'll just stop it after a certain period of time. It just saves me because I'm a bit lazy to press a little cross at the top. But if I run this again, we see here that there's these white lines that appear, and that doesn't appear on my laptop, but it does appear on a wide screen that I've got here. So I was going to go through and troubleshoot this, and the first thing that I did in order to, so really what I want to get to is this M-body simulation of galaxy mergers, and I'll try and go through the code of that, to release what happens, the physics of it, which is basically that I intend to make some kind of particle, or like a whole bunch of particles which represent stars in the solar system, and they've got positions X, Y, and Z, although for the purpose of PiGame I'll only be using the X and Y components, and I'll probably zoom in on this as well, Control Plus, just to make it a bit bigger while I'm going through that. So yeah, there's a position, but there's also each planet can have a speed, and it can have an acceleration as well. It can have a force applied to it, and it can have an acceleration. And it did grind a little bit slower as well, and possibly because I did too many, or I'm not doing my calculations as efficiently as is possible. So I was kind of like working on, I've done kind of like the basics of it, and it was running quite nicely on the laptop, but it's running less nicely on a wide screen. So I'll basically be going from that point. So apart from the position, I also created this other vector, or this other object of this class basically, and I called it space 3D, but it actually looks exactly identical to this position thing. And basically the reason why is I created an acceleration one, so you've got positions, and then you've got velocities first, and then forces, and then acceleration. So and each one is a 3 spacing, but then it's not needed because they all look exactly the same, which is they got there's forces acting on each of these particles in the X, Y, and Z components. So go down, and here it is. So I then create a class for a particle, which is one particle, and it's got a position, and its position actually, and I changed them all. So even this one here, and I could remove it because it's like an unused class now. Its position has an X, Y, and Z component, and we can describe it like this basically. Like its component is X component is self.x, and its Y component self.y, and its Z component is self.z. And then each particle, again, there's supposed to be planets or stars in the solar system, so it should have a radius, and also it should have a mass. And if I did get this right, I would add the extra part in, because the physics of it is that the mass and the radius are effectively related to each other in some way, because the larger the object, the more massive it is. But then you'd have to consider like a density or some kind of factor that linked mass to radius. But for the purpose of modeling, you could sort of like just, at least for the purpose of visualization, you could use a radius, larger stars, bigger radius, and smaller ones, smaller radiuses, which is exactly what happens. You can see on this thing, if I hit F5 again, apart from ignoring the lines that go across, that you've got some big ones and some small ones. I'll just let that expire on its own. And then, but you've also got a mass, and the mass will be used for physics. Again, the radius, you might use it for the purpose of collisions. PiGame will handle collisions in some way. I've not done it on this particular project yet. I've done it on another project. And then we've got a velocity. The velocity is, so the velocity will cause a change in position, which is distance equals speed times time. So if you know the original position and you know how fast it was traveling and how long it was traveling for, you can work out a final position. And then likewise, we also know the force acting on the object. And again, it's going to act in the X, Y, and Z components. I initialize it here to 0, 0, and 0, saying there's no forces initially, at least for the purpose of calculation. But then afterwards, there will be forces, because you've got the force of gravity. And we're going to compute that force of gravity and attempt to model it. And that force produces an acceleration, and the acceleration is using force equals mass times acceleration. So we're using F equals ma over there. So if we know what the force is and we know what the mass is, we can do force divided by mass is equal to acceleration, like that. So we'll be using that formula basically. At least that's what this model attempts to achieve. So just scrolling down a bit further, what else is there? Okay, as part of the class, if you want to print your class, you've got this representation, and it's like prints out this nice thing at the end. And actually, if I was to uncomment some of this, maybe there, let's have a look. If I uncommented this and uncommented this, I think that might print out some stuff. F5, run it. We'll see the same thing run through. I can even close it early by the cross there, closed it at loop 117. But I think now we would have, yeah, it prints this out here, particle number 4. I don't know, it prints out all of its position, and this is basically all of the data. So I think that was its initial position. I'm printing, like, I just created something there just to see what will come out. But we've got a radius here, a mass, we got its velocity in the X, Y, and Z components, we got its force in the X, Y, and Z components, and we got its acceleration in the X, Y, and Z components. And again, the acceleration, we'll see that as I scroll down below, but the acceleration will change the velocity. So that's those are the initial classes, but then and we've got our particle, and our particle uses the classes above, and then we have our actual system itself. So I initialize this system, and there's a couple of things that we need to do. Let's just I guess go through them at one point. Right, the first thing that I do here is make particles, because, and it's kind of like you could sort of like create your own sort of version of them, but as a first guess at least, or as a first stab at doing something, let's just make a whole bunch of dots on the screen, which is done over, where is it, on here. So I make a dictionary here called particles, and it's like an empty dictionary, and each particle has an index, and that will be the key of the dictionary. So it's got like an integer number representing it. It's particle 0, 1, 2, 3, 4, and so forth, however many you've got. And then it's got this particle class, which is all of this here, which is everything that you need to describe a particle. So it's quite a nice way of passing passing data across. So that's basically what will come out of this make particles function. And because it's I think like we're now talking about like kind of like it's still structured data, but it's not flat anymore in terms of you've got a key and then a value, but the value is itself a dictionary because it's this particle object, and the class effectively contains a dictionary. It's a dictionary of stuff. But what do we actually do? We go we say like we're taking this argument n, and n is going to be the number of particles, and then we're going to do this loop for I in range n, and then we're going to give them some positions in space, and we need to give it an x component, a y component, and a z component. So there's 3 of them, and I've just said, well, let's give it a random number between -100 and +100 around a centralized point. We don't know what that point is yet. We'll get to that, but basically at that point is some part of our window, and we want actually that point to be the middle of the window. So if I F5 it, basically where my arrow is, that midpoint, we want it to be here, and PiGame windows normally are at the top corner. So there's a way of dealing with it, but we've kind of like just said, just uniformly distribute them randomly between plus and 100 minus pixels from some center point is what it's going to be. And also, I thought I'd put this in just for an extra kind of like little test here, which is we'll give them all an initial velocity as well. We could say that everything starts at 0, so it's all static, but if it was all static, but it's a good test case to do that, we'd see everything collapsing in, so all the stars would move towards each other initially, because they'd be the only force acting on them, or the only motion that would come from them would be from the forces acting on them, because they had 0 initial velocities, and therefore everything would be inwards because they would all be going towards the center of gravity. Likewise, each of them, we just said we'll give them a mass. Again, it's a random number, somewhere between 1 and 100. I wasn't sure about 0 mass particles, so I thought I'd leave them out. And we might break something, as in, again, we have force equals mass times by acceleration. But of course, if we want to work out an acceleration and the mass is 0, so we'd have divided by mass over there. And if our mass was 0, we'd have a number divided by 0, and we'd have an infinite acceleration. So we'd have created some sort of black hole in our system. We'd have created a singularity which would break our system. So we're kind of like avoiding 0 mass particles. So we're assuming all of our planets or whatever are of decent mass. And again, this is a bit of a weird one because I just put in a radius, and that's more like for the optical effect of it at this point in time. The radius and mass aren't connected in any way, but it's like, so you could have a small particle, a particle of size 1, because randomly could be assigned that number, but it could have also been randomly assigned this very high mass. You could think of it as, I don't know, like a very dense meteorite. Might be that sort of thing, whereas you might have a gas giant, so it's got a much bigger radius, 10 times the radius, but like no mass because it's like made up of a lot of gas and so forth. But anyway, once we've done all of those, so that's the kind of like the physics of it, we say this particles I, and that's this integer here. So each time we loop through our for loop, we get this value I, and then we assign the particle all of the components that it needs to be assigned. So we assign it its position, we assign it its radius, we assign it its mass, and we assign it its velocity. We don't need to assign it, and if I hover over it, we don't need to assign it the force and the acceleration, because we've just said if those keywords aren't there, then just stick in values of 0 for all of them. So they got no initial forces and no initial accelerations. Although immediately on the first cycle of the calculation, they will have forces because there will be the force of gravity acting on them. So that's basically it. So we make our particles, and then we just return particles. And this little part here at the top is telling us what's coming back, which is, again, if we hover over it, well, it just says dictionary here, but it's also telling us it's a dictionary, but the keys are integers, and they're our labels for the particles, like our unique reference numbers for each particle. and then the particle is actually all of these details: the position, radius, mass, velocity, accelerations, and so forth of the actual particle. So that's what this particular function does. So we make our particles. I was then trying a particle history, but I didn't get that far, so that's going to be left for another video. But basically, you can actually store the positions at each iteration into like a dictionary or a list. Python lists aren't that efficient, and that's probably I think a dictionary is more efficient, but potentially that might be what has slowed down my that did slow down the system, because if I put in a lot of stars, it would actually have slowed the system as well. But anyway, there's that. So that would be useful, because if I wanted to track one particular star, which I do to make sure that it's kind of like rotating or moving in the right type of pattern, because we're expecting that Newton's laws apply to it. So if it's going at a velocity, like at a certain speed, and it's being acted on by a force, so that force is pointing towards the center of mass of the particles, which we'll get to next. So it should create this curved effect, kind of like either spiraling in or curving around it and sort of shooting off to infinity, or if we were lucky enough with the mathematics, forming like a perfect circle around the center of mass. But I've not seen that yet. But what is this center of mass? Well, we create this little function here. I will go to it, but so in order to calculate the center of mass, we need to know the total mass of all of the planets in the system, and then we sort of want to work out the average position of the masses in the X, Y, and Z components. Now, to get the total mass of all of the particles in the system, we just got this simple function here, and if we go to definition, here we see get mass, and all it does is it does for particle in self.particle.values, and I have to do it this way because remember that our particles were stored in a dictionary where the keys were the indices, and the rest of it, so the keys are the indices and the values are the particles themselves. So I'm iterating effectively through this list. This self.particles.values is a list. So it's a list of particles, and we're incrementing the total mass. So the total mass starts at 0, and we're incrementing it by the particle mass. And each particle has this mass that is between 1 and 10 randomly. So I know it's between 1 and 100 actually that was assigned to it. So go back to, if I do go to definition, I don't think it will. So I can go to references. It should go back to the reference, which was above at the top. Being very slow in doing so though. Finding references. I don't know why this has gone very slow. So I'll scroll back anyway. So we were at particles. There we go. Over there we were at the get mass. So and then finally we've got line number 103. So we can get the total mass of the system. And remembering that our masses are basically this floating point number, the mass is a float, but we set it in our, not in our system, but in our we set it in our create particles. So in our make particle functions here, so it was this particular number here that was that random integer between 1 and 100. It's the sum of the collection of all of those. So if we made 50 planets, it would be 50 lots of random numbers somewhere in there. So it'd be 50 times 50, which would be the mass would be roughly 2,500 units. I haven't even we didn't actually replicate proper planets at this point in time. It's just units at this point. And so we continue from there, and we want to now look at the center of mass. And how do we do that? We go to definition there, center of mass. And we set here, we go to, again, we're looking at each time remembering that we've got a dictionary, and the dictionary has the keys are just the index numbers of each particle, so particle 1, 2, 3, 4, 5, and this self.particle.values is the actual list of particles. So we're going to go through each of the particles, and then what we're doing is so we say that the mass times the position, because we want to get this weighted average basically. So this mass times by the position in the x-axis is it's like the frequency times the value effectively, and then if we divide it by the mass of the whole system, that will give us our average x position of the center of mass. And likewise, so we do this here, we do this sum here in this for loop, so these three things are in the for loop. We do that in the x, the y, and the z components. And once we've done these for loops, we can work out the total mass afterwards. But we had to at least iterate through this part of it, because we didn't know at each point where our x components, y components, or z components would be, because the position was randomly assigned. So we've definitely got to do that. Now, this, you could argue, is a calculation that doesn't need to be done every time, because the center of mass of our system, unless the system is moving actually, so maybe you could say it does need to be done every time, but if our system was static in the beginning, then the center of mass would be static, it would never move. Now, if we had on average our particles like drifting in some direction, then the and that we covered with the drift term above, which was, sorry, it's down below in our loops. But if we had that in our drift term, I wonder where I put that. Yeah, the drift is here in our velocity. So I've, like, if I created at the moment, on average, things might be drifting to the left, it might be drifting to the right. So like -10 in the x-axis, or +10 in the x-axis, and the same for the y-axis and the z-axis. But if we skewed it, so we just made it +10 to +20, there'd be like an average drift in a certain direction, and our center of mass would be moving. So that's what this computes, this particular function, and it computes the center of mass. So now, like, in terms of numbers of calculations, we have here, let's say we had 100 particles, and this is like back of envelope. Let's just do quote. There we go. So we might have 100 particles, and then we need to go through each one of them. Now we're doing it in the x, y, and z component. So we've got the x, the y, and the z component. So we're automatically multiplying it by 3. So we now have 300 calculations over there, and that's in this loop here. So we've got 300 calculations, and then there's a couple of extras, but we don't need to add them. So that's the amount of computational complexity that this is doing in any one cycle. So that's not too bad, to be fair. Computers should be able to handle that relatively quickly. We hope 300 cycles in a calculation. Now we want to move the particles, and we're going to do a similar type of thing for the purpose of moving the particles, which is that we use, well, I've actually listed it here anyway, distance equals speed times time. And we know our starting position because it's whatever the particle position, like x was in its x direction, y in its y direction, z. So it's got a starting point. And if we know the velocity in each direction, so we know the velocity in the x direction, and we know what like one time step is. Again, I've set, so like, it's just an arbitrary time step that I believe, where do I actually pull this in from? Well, itself, it's created in the actual class itself. So here at the beginning, we've got time step. So in fact, one thing I need to just, for consistency, is I just changed that actually. N is a number of particles, and time step is a unit of time. That's all. So all we need to know is a unit of time, and then we can calculate these steps that are on a change in position from that. So where are we? We're down here. So we know what our velocity is, and we know our time. Distance equals speed times time. This plus equals just means add it onto the original position. So we could do particle position. We could do this. Copy that is the original position plus these other bits. But this plus equals thing seems to be popular in most languages. Which means increment by that certain amount to add it on. And likewise, if it was going in a negative direction, so if it was randomly assigned this negative velocity, or even if it was started to accelerate negatively, it will go backwards. So it caters, everything is automatically catered for like using this plus. Everything's catered for because the directions, all of the signs take care of themselves, and this step like takes care of itself effectively. We'd need to know what our units are. So for example, we might be doing meters per second, and then we would be using we would want to use seconds as our time step. And if we did use seconds as our time step, we'd know how many meters we traveled if we were using meters per second in our velocity, and we could add that number of meters on to whatever our x, y, and z positions were. So that's what happens there. And again, it's looping through this same list, and it's doing 3 operations item in the list. So there's another, effectively, if you had 100 particles, you'd have another 300 calculations. So we had 300 from the from calculating the center of mass, and now we have another 300 calculations over here. So we're up to 600 calculations. And then we go on to the velocities, and again, okay, so now we're gonna move the particles. I don't know, we've done that one. Okay, so that's 300, and that's our second 300. We've also plotted out the positions, I guess, or created them. That'll be our first 300. So you can see that there's a lot of calculations that are happening, but it still should be handleable by a regular PC. Anyway, we move on. At this point, like if you know of a faster way, or maybe like one thing that occurred to me was when I'm doing these loops, if I'm always going through self.particle.values, surely I don't need to go through that and then go through it again. Surely I can do all of the calculations in one go, and that's something that I need to consider, because in terms of number of operations, is it more efficient to do one loop and all your calculations in one loop? So let's do the positions, the velocities, the forces, and the accelerations all in one loop, or is it better, or are you doing the same number of operations if you break it into multiple loops? So it's something that I need to think about in order of speeding it up. Because if it does speed it up, then I should be putting them into one loop, and I might have cost myself a factor of 4 in terms of computational complexity by not putting them all into one loop. Potentially something to think about, and answers on a postcard for sure on that one. If you've listened so far, that'll be interesting. Everyone who's listened to minute number 28, your views on that are helpful. So, and I have to have a think about that myself. But anyway, what are the changes on velocities? We know that the force due to gravity is, and this is like, from our classical Newtonian mechanics, the force due to gravity is this gravitational constant, which is actually this number, but again, for the purpose of computing, because I haven't put in planetary sizes, so I haven't got like these really, really large masses at the moment. I've just changed it to this number for the purpose of the simulation. But this is the actual gravitational constant, which is this tiny, tiny little number. But although it's a tiny, tiny little number, is acting on massive planets. So that's gravity, and that's why gravity, at least in our Newtonian mechanics, keeps things moving in circular motion, and that works relatively well for planetary motions. So it's this gravitational constant times by, notice the negative sign here, and the reason why it's negative, it means it's pointing towards the center of mass, effectively. So like if you think of the Earth and the Moon, we like to think that the Moon rotates around the Earth, but in fact what happens is they're co-rotating around the center of mass, and just coincidentally, because the Earth is so much more massive than the Moon, the center of mass lies somewhere around where the Earth's position is. So it doesn't lie between the two particles. And if we looked at like a binary star, where two stars are of the same mass, the center of mass will actually be directly in between them. So and then they would sort of like spin around each other, they co-rotate around each other. But anyway, so long as we know what the mass, I've used big M and little m, but it's actually M1 and M2. It's big M and little m is where you talk about like, one big object like the sun, and then a smaller object like the Earth. But still we differentiate the two masses. It's mass of particle one and mass of the mass of one particle, and then mass of the other particle. And here for our big M, it is kind of like true, because the big M represents our total mass of where we attribute the center of mass, which is the sum of the entire system. So this M here actually is a truly big M. It is much bigger than all of the masses individually collected, assuming a roughly even distribution in terms of like the sizes of stars. If you have a massively outsized star, then that would and if what we allowed in our random numbers, to go from 0 to like 1,000,000, and then all of the numbers were really small and 1 was really big, then everything would rotate around that one planet or like star or whatever. But anyway, there's an inverse square law in Python. Just remember that it's squared is r squared, so I was careful just not to do that, because I might do that in a great code somewhere, because we see r squared elsewhere. But anyway, I just do power, and this is the r squared bit, and this r is the distance between any position, so the center, so the x point of any planet, and the center of mass. So it's the distance between these two masses, this small m and this big M. And likewise, that's true in the y and the z directions. So we now calculated our forces, and from our forces, and I do this in one loop, and the reason why I do this part in one loop is kind of like we know straight away the forces are useless to us on their own, in terms of the useful part of the force is that it gives us an acceleration. So we can now calculate an acceleration. The acceleration is force divided by mass. So if we now know all of our forces, we can work out all of our masses. So if we've got 100 particles, we've got another 300 calculations. So that took us up to 900. Then we've got another 300 calculations, because we need to work out our accelerations, which so we're at 1,200 calculations, and then another 300 calculations, so we're 1,500 calculations for 100 particles. It's like 15 times at the moment. However many particles we're doing, that 15 times that number of operations by the looks of it. And the final, so we can work out our accelerations, and from our acceleration we can work out the change in velocity, because acceleration is dv by dt. The acceleration is the change of with respect to time, right? So, and we know, which is delta v divided by delta t, but what we do know is whatever velocity we had, if we've accelerated in that same velocity direction, so here's the x component, let's just pull that up, just got to be very clear on this, but here's our x component here, and we're talking about accelerations in the x direction for a particular time step, then we will then we know our new velocity. And again, we use this plus equals, and likewise, we do it for the Y direction over here and the Y direction over here. And finally, and again, you could say like I'm doing too many computations because I'm doing this third one and we're never really using it because we're displaying it at the moment in 2 dimensions. So you could say, well, you could immediately reduce 1/3 of your calculations by removing these Z components, and that would be true. Unless you're planning to use them. I was hoping to use them. I was hoping to make further ground and use them. But so that's what this does. So we've worked out our changing velocities as well. Now, I had this record particle data, which I'd have liked to have done, but I've commented it all out at the moment. But basically, I wanted to be able to track one particle, and that I'll have to get round to. And in order to track one particle, I need to keep an array or a list or something of the positions at each point in time for that particular particle. Because when you draw the screen in PiGame, and we're going to see this more obviously when I move across to the test PiGame, what the screen does is it keeps on effectively re-refreshing and drawing over itself. So if you haven't stored the entire history, then it's only going to draw the last points. So, and again, I was going to plot the path of it, but that part's not been done yet. Now we move into this simulation. And this is a bit where we will kind of like jump across because it's probably a bit clearer anyway in like some test things on PiGame. And I've got the PiGame thing. Well, I did manage to pull it up somewhere, so hopefully I'll be able to pull it up again. But if we go over to PiGame over here, because you can see I've been there anyway. Project, maybe I'll go to the documentation even. Yeah, go straight there actually. I initially did this one here, but basically what happens in PiGame, and I'll zoom in, so I think I can just do that. Yeah, there we go. The important parts in this, so you do a pip install of PiGame in Python, or pip3 install, or pi-m pip install PiGame. You'd have to do that to install PiGame. But the important part of it is this bit here, and this is the true for all of these types of things, whatever you're doing in animation, you need to get some sort of gaming loop, a game loop running, right? Which is like, imagine like a little flick book where in the olden days you'd like draw a matchstick man and then you flick the next page and that's how you get the motion. So what happens in all of these computer graphic things is you keep redrawing the screen. Now there's different things that you can do because you can like draw just parts of the screen that need to be changed, and again you get efficiencies there. If you just had like a sprite moving across and nothing else changing, you wouldn't necessarily want to redraw the whole screen because that costs you in terms of time. But they give you this basic game loop, and I actually did go in and in fact I did copy and paste it all into my code. So if I go back to the code here, yeah, because my thing wasn't working properly, I wanted to get to the point where like I need to debug this, right? Which is, why does it work really well on my laptop, but why am I getting these lines? And my hunch is that I've got a widescreen, like a 50-inch widescreen monitor, and on my laptop I've got a regular screen, and somehow that's mucking around with the settings. So I need to make sure that I get the settings correct for every screen. So I might need to rebuild from the beginning, possibly. So I created this new module because I need to test it. And actually the first thing that I'll do, and the first thing that I actually did, was I took this piece of code over here and I copied it and pasted it, I think nearly one for one, into here. I'm not even sure that I bothered changing anything because I just wanted to make sure that the standard code was working. Now I've put it into a function like this, whereas here it's just it's not in a function, it's just in the original script. But the reason why is because I want to do extra bits. But apart from the function part, there's nothing else. I've got this test the game. I called it version 1 because I've done extra work on it below. But imagine that we were at, in fact, you don't even have to imagine. If I do, I could actually do it even here. Hash percent. We get the interactive Python. So I could kind of like do it like that. And this is the next bit. Oops. yeah, that's the next bit. So this is one cell, and I could actually effectively run this. So I could do all of this over here, and it would actually run it in the interactive Python. Actually, I'm just interested to see. I'm going to close the interactive Python because I don't want it, but I was just trying to run everything as normal, which is why I did it the other way. But you know, just to kind of like show, just make sure that this is run by doing control return. Oops, I have to do, I guess, up here. Right, just run this little bit. Now it's going to launch the Python kernel because I was running it in the console before. So let's just like collapse the console a little bit. It's doing this little bit of thinking. All it's doing at the moment is going to import pygame and this and that. So now pygame and all of that's imported. I'm going to actually just run the loop, and it did open it, but it's opened it kind of like to the side. All it's done is created this this screen with a purple background. That's all it's basically done. So we could use the interactive Python, but just because I'm kind of like, I don't need to in this particular case, so I could do it for purpose of debugging. But I'm just going to do it like this, which is, I will have to switch off this one here again. I'll just comment that out. And now all that's going to happen is this piece of code here is going to run. So we are effectively going to be running this little script here. And we can kind of like see here, we've got this game.init, and I will actually type into, because I did before, but basically it starts everything up because it's quite a nice description, although I didn't take it from here. I went to Google Bard because I'm too lazy to. But in fact, I did it already, I think. I know that's between the update things, which was quite nice. So I'll get to that. But I could actually put it in here. Maybe I'll move it across in a sec. I'll just do the copy and paste. Copy. What does game.init? I'm literally doing this. Do in pygame. Right, it's going to effectively what it does is the initializations, but you can sort of like see it in Bard. So hit return there, and I might even zoom in again, just because I'll make it bigger and zoom in. I think just so that it's visible. Control screen bigger. But it kind of like tells us a pygame init function initializes all of the pygame modules that have been imported. This includes modules for graphics, sound, and input. So they're the three things, and actually it did say somewhere else that it gives you a 0 if it's initialized correctly, and a -1 if it's not initialized correctly. I actually had that on the I wonder, because I thought, no, because that's a display.flip, that's different. I was on that's at the end of it. It says it returns a tuple of 2 values, funny enough, but last time it said it returned a tuple of 3 values, so that's a bit of an interesting one. But one way or another, it's doing the initializations. I could sort of like go into it and have a little check. Maybe it will be in the documentation too, but it's doing the initializations to make sure that everything is set up. And I wonder if actually on the documentation there, let's have a look. If it describes the init over here, we'll be doing the second example anyway. Tutorials, introduction. Okay, several modules are not included. Some modules are not included in all platforms. Sprite. Okay, it hasn't got it yet. We can go back and have a look, but the initialization at least needs to be done all the time, and it's basically making sure that that the video at least is set up, the video and the sound is set up properly. I actually thought, or at least it did mention that an extra bit was there as well, video, sound, and something else. But that's what that initialization part will do. So we just go back to the code over here. and then we've got this screen dot display dot set mode, and what this does is it actually sets the size of the screen. And quite often in the code you see something like, you see it actually in capitals, but width and height equals you know, these numbers here, this number here, and 720. Right, you'd see something like that, and then, you know, the user can choose to put in a width over here and a height over here. I'm not going to muck around with this at the moment, just because this is our tester, and it's just sort of like, I just want to make sure, I want to get to the point where I can verify why I'm getting those white lines. So this is the piece that's annoying me, is these horrible white lines that I need to get rid of here in the running of it. It's really annoying. You know, why do they occur? So I need to get rid of those white lines. So anyway, we're back at our PiGame. So we've set our screen size. It's 1 to 80 pixels wide, and that's how high it is, the 720 high. And then there's something called the clock, and again we can sort of like ask what the clock does. But basically what the clock does is it makes the so we initialize a clock effectively, and then it makes the frames per second the same number of frames per second, so that if our processor was running a bit quicker or a bit slower, that it looks quite continuous. Otherwise you'd have things that are a bit erratic across the screen basically. So that's what the pygame time.clock does. And again, we can sort of like ask the question in Bard here. You know, it's not the best way. The best way is going through the documentation. I'm just doing it because I've got the docs open. I've copied and pasted something. What does do? The reason why it's not the best way is sometimes these AIs throw things out when it becomes a bit more technical in the analysis. They sort of like go and get these conventional things in their large language models, and they throw things out just to make you happy. And that's what I was mentioning before about the init thing. It told me two different things. Now here it says, let's just try that again. What does pygame.clock in Python for the PiGame module? I'm going to help it search through. There we go. I don't know if it will or won't come out with an answer. You know, it might come out with an answer that keeps us happy, but I don't necessarily always. I do use it quite a bit because I don't know. It's got sort of like lazy sometimes, but it's kind of like relatively helpful. But you just got to be careful. But let's just see what it says here. The pygame is function in Python for pygame module. So now it's found it creates a clock object that can be used to keep track of time. The clock object has several methods, so hopefully it's good. That can be used to get the current time since the clock was created. I'm not sure that's correct, because that's what the time.time thing does in but you know, in Python in general. So like you might have just imported time and done that. But here is something a bit more useful. The most common use of the pygame.time.clock is to limit the time frame of the game. This can be done by calling a tick again. Do we? I think we do use a tick actually in here. Yeah, we do clock.tick, so that's fine. And it's the number of milliseconds that have passed since the time was called. So I'm not even sure that that's 100% correct. I thought it was a number of flickers per second, so that might not be. And actually, it looks like it's possibly contradicting itself here, but number of frames per second is what you're getting here in your clock dot. So that tick isn't milliseconds; it's number of frames per second. But anyway, we've got a clock type object is what we do know, and if we make this a higher number, it's more frames per second, and this is probably a better way to go through it, which is documentation. So it limits it to 60 frames per second. So if we had a higher number, we'd have a higher refresh rate, So we could go at like 120 frames a second or whatever. Now, the next bit here is we say running equals true. This is a very common pattern in Python because we're going to go into a while loop. So we do while running equals true. Okay, and this is always true because there's no point that it's switched to false unless we've got this pygame.eventtype.quit. And I think that's where you press the X button. Yeah, the user clicked X, so it's looking for you to press the X button, and that's it. And then it goes false, and then this while true loop exits, and it finishes the loop. But here's the one bit that we do see, which is we got this screen dot fill purple, so we're filling our screen purple basically, and this part here actually is probably the important bit, which is, it says render your game here, but we're going to basically be doing all the code, all the graphics, etc. and code go here. Anything that you want to refresh and redraw at the screen at any point in time is going to go here. And then here there's a little function at the end of the while loop, or second end to the while loop, which is this game.display.flip, and there's actually also a game, because I didn't know this, or game, how about spell it, pygame, pygame.display.update. So there's that, and the question is, what's the difference between the two? And this flip one refreshes the whole screen. I know the answer to this because I looked it up. The flip one refreshes the whole screen, whereas the update one gives you the option to update only a portion of the screen. Now, in our case, we need to update the whole screen because we're talking about stars, but it might give you some speed advantage. And I kind of like found that I wasn't like wholly wise and knowledgeable. This was, I looked it up. So I was scrolling there, I looked it up here, kind of like, oh, so what's the difference between flip and display? And it kind of like says that here. This one updates the entire screen, whereas the update specifies, uses a specific region of the screen. But actually, if you use the update and leave it blank, because I did, so you could do either or, so I could comment this one out. It has the same effect, which is if I hit F5 to run it, we're still going to get our purple screen that pops up, and nothing else happens. This is a bland screen, but it works, and I haven't got any horizontal lines flying through it. And this is the the point of, I guess, testing or making your code work. So we got that bit. Now I'm not going to run this anymore, so this function is never being called. I'll leave it in here for the purpose of having some code there. I won't even put this in the thing. I'll move out all of these. I'm moving out all those hash percentages because the interactive thing, I'm not going to be using it like this because I'm only testing. But I went on to, so that was the first one that worked. I go on to the second one, which is this here, which is a slightly more fleshed out example, which shows you how to move something, a circle in this case, around the screen. So I copied and pasted all of this piece of code further down, and it even lets you do some key presses all the way there, and I copied that, Control C, and I can pasted it into the code over here. And it worked off the bat really well, nice and fine. And I was like, that's great, that's fantastic. And I could actually move my particle as well. But I was like, okay, now I want to start changing a few bits and bobs and making it look more like my simulation. And what I might actually do for the purpose of fixing is, and you'll see this in a second, because when I do run it, this works. And this is why I was talking about computational complexity as well. We have exactly the same game loop. We sort of like do our setup in some way, height, width, start the clock. So we do initialization, then we make our screen. The screen is a certain width and height. Then we start the clock. This running equals true. We do that. I actually added an extra bit, which is a counter variable, because I might want to see how many loops I've gone through. At least I did that in my, if we just go back here in the end body simulation, I'm just interested to see like if it was struggling or not. So F5 to run it again. If you look at the top corner here, we can see the loop counting. over there. Like you can see that counter, and then it, like when it gets to 250, it stops for me. So it's just something to see each loop iteration. So, and I did that by putting a counter function in. So I scroll down, and so all of the stuff, I'll make it smaller for a second, just so we can see the patternage of it. New word, patternage. I wonder if I can do a split. I don't know if should I do a split screen? Split left and right. There we go. Split right. Now I can move this one up, and I'll do a control plus again. Okay, it goes off the end, control minus. What we can see, at least I can draw this, is here's our function over here, and there's our function over there. So that's where we kind of like started the function. And I obviously call this game one because you can't have two functions named the same thing. And here is our setup over there. So we've got this little setup block, and all of that happens before the while loop. We don't want to be doing these things inside the while loop. Anything that you do inside the while loop is going to run, at 60 times a second, basically, because this is this clock dot tick, or limiting it to 60 times, but it's going to run through this while loop at some super fast speed if you didn't have this clock dot tick in there. So here's the same thing. This is just a setup, and I've added a few extra bits in there. And the extra bit that I added was, so I'll make this one a little bit bigger because this is all before the while loop. So I added a couple of extra bits to start with, apart from what was given. Same screen size. I put in a caption. So I added, let's add this extra bit there. I added this bit here. Didn't seem to have any particular bother. It does that all nice and fine. And I added in a font over here, and you'll see why I added the font there as well. And in the code, and I added a run, not the running equals true, but I added a counter over here. The rest of it is actually taken from the code, and what they do here is, and I actually did this. This is very standard for PiGame, but if you want to work with the middle of the screen, then they actually did this get screen width, but it's actually this 1280. That's the width, and the height is the 720. But the middle of your PiGame screen, if I was to draw the screen, so I could select, attempt to draw a screen just over here. Like there's our screen. 0, is here, 0, and this is the full width and height, W and H. And here is all of the width, so W, but the height is 0. And here is all of the height, so the width is 0 and the height is H. So it's 0, H down there. They're like the maximum coordinates, but halfway in between, this bit in the middle is a half of width, and it's also a half of the height. Not the world's best writing, but you get it. Half of the width and the half of the height. So that's what that is. Let's just, if I hit undo enough times, all of that will disappear. I've reached my maximum number of undos. Okay, I'll get rid of it all, and I'll start drawing again. But so we've got our pre-loop stuff that's going in over there, and there's our pre-loop stuff that's going in here, and then we've got this while loop over here for running everything. And the while loop is the same for both of them. And at the end of the while loop somewhere, I won't draw the full bit of it, but we get to this bit, and I'll do the same bit here. At some point you get to this display update or display flip, whichever one we were to choose, and then after it, then it's doing effectively the refresh. So it's doing, let's say, the second part of the loop here, and here it's doing the second part of this while loop, like the updating part of it, and then it goes back to the start of the loop. So that's basically what's happening, and finally you've got a quit at the end over here, so you get out of it, and a quit here, it terminates. So these things are exactly the same patterns, and this is always the pattern that we're going to be invoking using PiGame every single time. So I'll get rid of all of that and go back to the arrows, and I can now move that, and this is our modified version. And I'll just zoom in again, so Control plus enough times on it. Without having to know too much and without having to be too much of the expert on it, you can sort of like go here and it tells us what's going to happen. Here's a slightly more fleshed out example which shows you how to move something, a circle. Well, that's fantastic because all of the things that I were doing, all the planets were circles around the screen. So I was like, okay, I'll test this one. And this is the loop and everything. And I made mine a bit more elaborate, so mine's got a little bit extra added onto it. But here it's looking for, or at least it does, where is it? Pygame.key.get, but yeah, it's looking here, it's setting these variable keys and it's looking for something extra, which is pygame.key.get underscore pressed, checking for a key press. And if you press the W key, you'll move one way, and the S key, so W, S, A, and D are common gaming keys on your keyboard if you look at them, but you could have used the arrow buttons, I guess. But anyway, I'll work with that. That's perfectly fine. And then it does the same thing, this display.flip, or like I use this display.update, and then it's got this this time delta thing in it. And here, so we limit ourselves to 60 frames per second, and that's our 60 frames per second. DT is the delta time in seconds since the last frame. Used for the frame rate independent, used for frame rate independent physics. So that's kind of like how you get your time in seconds. So whatever this is, yeah, and it's actually like I did actually run it and test it. It's about, well, the calculation, if you do 60 over 1,000, it gets you to, because I did it here. In fact, I still got the answer. 60 over 1,000 is 0.06, but when I actually ran it on the PC, it was actually a bit faster than that. It was 0.016 or something. So it leads me to believe that this clock tick 60 isn't exactly, well, it might be 60 frames per second. But anyway, that's fine. We can go, let's go through and look at the code, because now we can see it running, which is over here, and I can just press F5 to run the code. Now I put in some random numbers and some extra bits and bobs, so it should pop up somewhere. Why is it not run? It's not run because I have not called the game function, because I commented it out before. So let's uncomment it again and run. And okay, I put in loads of yellow dots. Yellow dots weren't the original bit of code, but I wanted to simulate something. And you can see the loops here, so my loop thing. But what we do see is there's no white lines going across. Now, I don't leave this on too long because I get going blind. Like, it's done like 1,000 loops now, and we can see, so like, you know, how many loops it's doing per second or whatever. You can count the number of seconds, and you're expecting to get 60 frames a second. But anyway, what did I do that was extra was this little part here, because I did a couple of things. First of all, that purple screen was really killing my eyes, and it wasn't like helping me. So I turned the screen black, and I did this white. I turned their circle white, so it's a bit more visible. I actually should run it again. I'll do F5, because this has one advantage, which is this circle actually moves. So if I press W, the circle goes up, and if I press S, it goes down. So you can sort of like move your little circle around on this screen. So it gives you, that was the extra bit. I don't have that in there. In the code that I'm running for the simulation of the galaxy merger, because there's no point, because there's no need for it. Although if you had a spaceship, then you could sort of like put it in there, and or if you had some big object that you wanted to fly through the galaxies, that'd be interesting, that you wanted to manually control. So that, me moving that came from here. So each loop is checking if the key is pressed. If you press a certain key, it goes down or up or whatever, you know, and it calculates a specific moment based on this time step, and the time step is based on the clock time. So that's kind of like what that all of that was there for. But I'll just print random like circles on the screen as an extra bit in that code. So I just added it here for eye range, and I did 1,000 circles. It's less blinding if you sort of like do 100. There we go. It's much less blinding. Maybe I'll do even less. And you can sort of like move it around. And This will presumably use less processing power. In fact, I could sort of like run that as a separate thing as well. Let's do 10 F5, so it's really clear and obvious there. So it's much more sparse. Notice when I move it, it's on frame 178, and it sort of like freezes at that point when you click it and capture it. And we see it says here embody simulation. That was me just putting in the title screen, which was this bit here at the top, embody simulation. And it's just going to keep running forever. Again, I could put in an if statement somewhere at the end, like if I'd need to put in a counter function. Did I put in a counter? No, because I've got to try and mimic as much as possible. Also, I did put in a counter function here. I needed to put in a counter function because also I did at the end somewhere here I create this rectangle and some text which I must have created over here because I have to create it somewhere in a loop because the counter number keeps updating, so I can keep updating this text thing here. I could put all of the text together, so like take all of that, and maybe I should put it all together because it belongs all together, and so like paste it over here. This is all of the text stuff, which is basically, you know, if it was like in terms of the text stuff, right to the screen. And all it does is create this rectangle at the back. PiGame.draw rectangle. It makes this dark rectangle, and then it does screen.blit, which means it writes to this rectangle the text, and yeah, so it gets the rectangle itself, and it writes to it. So and it writes to it, then writes our text, whatever the text was. And this should run just as well this way round with everything there. We can see that it does because our loop is over there, and we can see this dark blue. I created the dark blue, which was this colouring over here. So we just say where to write it to, screen. Everything at the moment is screen. We've got one screen that we're talking about, and this is the colorization, and it's just RGB 0, 250, 0 to 255 for each of the parameters. Red is the first one, green is the second one, and blue is the third one. And if I use 255 over here, then it would be like a bright blue. So I just wanted the dark blue, so I did roughly half of 255. And that's it really. So that all works, and it tests and it runs. And then I was like, well, you know, I can sort of like run this at maybe if I put in more dots, maybe it'll break it then. So it hasn't broken it. So I've got this working here to a relatively good degree, but on my wider screen, I get this problematic set of lines. So it's doing the right thing potentially, but it's those lines at the end, so it's a little bit annoying. And what I'll do here actually is the same thing, which is this clock.tick, which is we can do it at any point. I guess we'll do it at the end. If I'll put it before the clock.tick. I even put it before the update, although we'll never get to the last update. Basically, your choice as to where to put it. I'll put it after the last update, so you got your. But basically, over here, if counter, I could say is equal to, because it'll always pass it, but I always try to be a bit safer. It's greater than or equal to 250. Then what we were looking for before in this while loop, this running variable, we just want to say running equals false, and now it'll only run 250 loops like this, so that I don't have to manually close it, and I can be a little bit lazy and talk about it while it runs in the background over here. So here it's running, and when it gets to loop 250 it'll close itself down. That's all. So that's basically it, but I'm going to need to put the physics in, which is basically the particle positions. I'm going to try and do it again, and I might attempt to implement it into this PiGame loop, which I took straight off the web, compared to constructing it myself, although the construct is exactly the same. So I have to think about it a little bit more cleverly, and I'll keep on adding each component until I either get the white lines or I manage to resolve the white horizontal lines to get them to disappear off the wide screen. So it's either a function of the screen in some way, and it's quite likely to be that, because if I didn't observe it on a smaller screen, like on a laptop screen, then it's possibly my screen rendering, and maybe there's things that you can and can't do about it. But you do want to be able to see your images or your visualizations on any screen that you open it on. And I was actually quite surprised, that did pop up and to create this error, because it's one more thing that I didn't need to see, because it was all working quite nicely, and I wanted to get on with the physics and make the physics of it a bit faster and track the particle and so forth. But that's basically it. I think I'm going to leave it here just because it's got to the hour mark, which is more than enough, and a lot of things are learnt at this point, and hopefully we'll get a bit further with the n-body simulation of galaxy mergers in Python. We did a lot of the physics. We did a lot of PyGame, which is the screen graphics of the physics, and that's it. We'll leave it there. If there's any comments, if you do want to like this, by all means like it. And if you can follow, that'll be fantastic as well. I know I've said it after an hour, and I probably should have said it at the beginning. But if you do follow, it's extremely useful and helpful. And if you do like, it's useful and helpful. And certainly, if you see errors or better ways or things that you could do or questions that you have as to how this could be improved, by all means, put that into the comment section as well. So that's it. Thanks. And yeah, that's PyGame and an n-body simulation, attempted n-body simulation of a galaxy merger.